SwayamPrabha. Digital India. Educated India.
Dear learners, greetings from IIT Guwahati. We are in the MOOCs course Power Plant System Engineering Module 4. The title of this module is Hydro and Renewable Energy Power Generation System. In our previous discussions, we elaborately discussed about hydro energy, wind energy. Now, in today's lecture, we will focus our attention to harness energy from oceans. So, in this lecture we are going to touch upon the following topics. What is the concept behind this ocean energy? Because ocean seas, they are characterized with its wave pattern as well as the temperature difference that occurs on the surface of water and the deep water. So, this particular concept, we call this as a ocean temperature difference that normally happens throughout this world or earth. Now, by virtue of this ocean temperature difference, one can think of the concept of heat engines to harness power from the ocean waves, and that particular segment we call that energy harnessing from oceans. But there are thermodynamic viewpoints to this, because to harness the energy, when we are using specifically working fluid, there are two ways we can think of this harnessing the energy, and because this ocean temperature difference is typically low, and based on this we have proposed two thermodynamic cycles, and they are called as open cycle OTEC systems, means ocean temperature energy conversion systems, and closed cycle OTEC systems, and they have given a name. We call this as a open OTEC system, we call as a Claude cycle. Closed OTEC system, we call this as a Anderson cycles. In fact, both the cycles are modified form of ideal Rankine cycles, and when you deal with these cycles, effectively it is known that they are called as low temperature cycles, because the temperature difference which is available to us between the ocean surface and deep water is less. So, we will touch upon these two cycles briefly, but main intention we will see that what is the concept behind this ocean wave energy. Now, previously we have in our syllabus we have covered mostly on steam power systems. Now, if you look at this particular figure which we have shown in our module 2 in the beginning of the lectures, that figure talks about three major parts. One is this region M, and that is nothing but the supply of energy from the working fluid. It can be fossil fuel, nuclear, solar and geothermal. Now, when you dealt with steam power systems, our main target was the use of fossil fuels. We never bothered about any other resources. Now, time has come when you say we want to harness energy from ocean wave, then we have to think about the other sources, and mainly this concept of ocean waves energy is a kind of a passive mode of solar heating. Then other parts like we have region N, which is this energy conversion mechanism, that is heat to work. This is nothing but your heat engine concept. Then next part is your electric power generation, that is you need to couple with electric generator, and last part is supply of working fluid to this power generation systems. So, the choice of working fluid is also equally important when you dealt with the low temperature cycles. So, we will see these their importance. Now, if you refer this temperature entropy diagrams, now for a conventional fossil fuel based steam power systems, our working fluid was mainly water, and to get the advantage of water, we bring this water to the maximum possible heated locations, that is towards the superheated regions. Then only the steam has maximum potential for to be expanded in the steam turbines. So, point 1 dash normally for fossil fuel based power generation system, that is steam power systems, we start this turbine process or expansion of steam much above this saturation line or saturation dome. So, that means turbine inlet condition mostly falls in the superheated regions, and we try to expand the steam to the best possible extent. So, this is the dome region what we say we use in the for steam power generation. Okay. Now, when you dealt with low temperature systems, then we do not have options to go to the superheated regions. So, we have to somewhere inlet for turbines to start from point 1, and that is nothing but it falls exactly in the saturated vapor regions, and we try to expand the steam in the turbines. This is one part. Second part, when you dealt with the steam power system, this temperature difference delta T, that is at steam generator pressure and condenser pressure, is very high. Very high means it is we need to delta T, we can keep it as to maximum delta T possible for a fossil fuel based plant. So, that we can typically go to the superheated region in much easy manner. But in case of low temperature power generation system, we do not have flexibility of this delta T to be much higher. So, typically this delta T is lower, and that is the reason we call this as a low temperature cycle. But both of them falls under the common roof, that is called as Rankine cycle. Now, when you deal with the low temperature cycle, then we call this as ideal Rankine cycle, because it says that you should start the turbine process ideally when we have when your inlet condition of the steam is almost exactly at the saturated vapor region. So, this is all about the low temperature cycle, but the advantage of low temperature cycle is that your resources, fuel resources is free. That is the reason, because fossil fuel based plant requires infrastructure and that there is a investment of money. But whereas when you say low temperature cycles like oceans, so energy from the ocean is free. So, for that reasons, to some extent the low temperature cycle becomes a lucrative option. So, if you look at a low temperature cycle, essentially speaking, we are looking a expansion process in the turbine when the steam is exactly at saturated vapor region and it expands to turbine. That is one aspect. Second aspect is the delta T. Delta T difference is less. That means, in this case it is 90. At this point, if your saturation temperature is 90 and your condenser pressure is condensation is occurs at 20 degrees centigrade, delta T is close to 70 degrees centigrade. But still this difference could be possibly lower than that. So, there are two possibilities to take into account. One way is that your working fluid can be same as that of the fluid which is available in the ocean, that is water, or the working fluid can be considered as a different. So, based on that, you like in this dome, you this particular low temperature source could be a ocean, and this secondary cycle we can have different working fluids, which means that we have a heat exchanger that taps the energy from the ocean, which is typically available at certain temperature difference, and use that temperature difference to power the turbines. That means, in other words, what we are saying, that heat which is getting released from this ocean water to the working fluid is utilized to heat it and to a condition which goes into the turbines. So, for example, if your ocean condition is saline water, your working fluid may be ammonia. It is a low temperature refrigerant which can use this, and this refrigerant only will give you the conditions in the low temperature cycles. So, this is all about the concept behind the ocean waves. Now, let us try to understand what is this ocean waves, where it comes from. Typically, if you look at the solar energy as the major source of major chunk of energy, and it is available in plenty, and we call this as a renewable form of energy. Now, under this single roof, we have multiple ways of passive energies available in our earth, mother earth. So, one way is that wind energy, and this wind energy comes due to uneven solar heating of earth surface. We have seen in our previous two lectures. So, how we want to harness wind energy? So, you have to incorporate the concept of wind turbines. Second part which is available, that when the sun's energy comes from it falls on the surface of water, the water on the surface gets evaporated and goes to higher altitudes, and in turn it comes as a rain in a particular locations. When there is a rain, we can store that energy in a dam, and through this process we can convert this energy from the water, and we call this as hydroelectric energy. So, we have wind energy, we have hydroelectric energy, and that we get it by evaporation of surface water by solar heating. So, one way, the solar heating causes the formation of wind or motion of air, and we call this as wind. Second, the solar heating also causes the rainwater, and this rainwater can be utilized by storing it in a dam, and through this conversion we call this as a hydroelectric energy. Now, rest two parts that we have is this. One is ocean temperature energy conversion, we call this as OTEC plant. So, here what happens is there is a absorption of solar radiations causing ocean currents. So, basically when the solar radiation falls on the surface of the ocean, the energy gets absorbed at every places in the ocean, and thereby what happens, the surface water gets heated, and whereas the deep water still is deep water does not feel the sense of heat, and through this process the energy gets absorbed through this water surface, but since the oceans are very deep, it cannot go much into the depth. So, which means that the effect of solar radiation is only felt at certain depth in the oceans and close to 1 kilometer or 1000 meter. So, during this depth or within this depth, we feel a temperature difference, and that we call this as a ocean current, because top surfaces have lower density, and below the depth of 100,000 meter we have a different temperatures. So, that way ocean currents we can see only below within the depth of 1 kilometer, but below that still the water is at lower temperatures. So, what means what we can conclude here, that if you go below 1000 meter depth, we have temperature of water which availability which is much lesser than the surface of the water, and that difference could be in the range of 15 to 20 degrees centigrades. So, that is the concept of temperature difference availability between the surface of the water and the deep water, and that concept we typically use this as a heat engine concept. So, let us see that when the solar energy falls on the water surface, what happens? It follows an equation called as Lambert's law of absorptions, which says that there is a decay or intensity of the radiation varies with the depth, and that is in the form of exponential nature. So, if you want to know the intensity of the solar radiation at the depth y, then we can say at the I y is equal to I 0 into e to the power minus mu y. That means, intensity of radiation falls down with the depth exponentially, with maximum being on the surface of the water, and this mu value depends on the nature of water, and for fresh water mu is 0.05, for turbid fresh water mu is equal to 0.27, and for salty water mu is equal to 0.5. So, higher value of mu means more less penetrations. So, of course, these are the some ways methods in which we say that how the intensity of radiation varies on the surface to the depth. Now, let us see what is the concept of ocean temperature difference. As I mentioned that if you say this is the surface of ocean surface, and we are looking at depth much below, that is y, and typically if y goes to 1000 meter, and we will get a temperature difference delta T. Now, often what happens, ocean surface is typically at 25 degree centigrade. Now, if you go 1000 meter depth to it, then we call this as a deep water, and availability of deep water is close to this T d is close to 10 degree centigrades. So, below this there is no further temperature down is possible, because the sun's radiations cannot penetrate. So, whatever ocean currents which is available, that means in these regions within the depth of 1000 meter. So, what it means is that we can imagine the surface to be a reservoir, and it is, we call this as a source, and the deep water we can call it as a another reservoir which is called as sink. Now, same concept if we introduce here in a heat engines, then what we say is that your source temperature is close to 25 degree centigrade and sink temperature is close to 10 degree centigrades, and in between we are using a heat engine. By extracting heat from the source and rejecting heat to the sink. So, this is called as ocean temperature energy conversions. That means, temperature difference is getting utilized as a energy conversion which is in the form of work. So, heat energy gets converted to the work. So, this is the concept. Now, here we have two choices. So, when you say heat engines, we have choice of working fluids. One possible choice is that same water can be circulated continuously to produce work. One is the ocean or sea water, and second category is that we use a different working fluids. different working fluids we are using for better performance. So, that way we say it whether it is ammonia, freon, this kind of refrigerant fluids that can be used for operational viewpoints. So, considering these two things together, entire things falls under two fundamental aspects, what we call as low temperature cycle, and second is binary vapor cycle. So, in the binary vapor cycle what happens? We are restricting the power generation using the specific working fluid, which is typically ammonia or freon, and but the heat exchange takes place as that is QH or QL, low temperature source or sink, that takes place by virtue of this temperature difference. So, this is all about the concept behind the ocean temperature difference for harnessing power or energy from the oceans. So, based on that we have two cycles, one is called Claude cycle, which is open cycle in which same working fluid is being used, and other one is Anderson cycle or closed cycles in which we are using different working fluids, like one for energy, tapping the energy from the ocean water or sea water, other is using that tapped energy and transferring it to the secondary fluid, which is normally expands in the turbine. And other possible limitations for this ocean temperature difference concept is that if you look at the geographical map of ocean water movement on the earth surface. So, this particular figure shows that locations where your equator, we have equator, Tropic of Cancer, Antarctic Circle, and this we call this as a latitude. So, we are moving along the latitude. Now, when we are moving along the latitudes, we see that ocean surface temperature is less at Arctic Circle and higher close to equator, and this temperature also varies across this month. So, in the February and in the August, these are the typical the maximum temperatures difference that we can get. That means, if you are at equator closely, we will have this much temperature difference in the month of February and August. Now, on a tropical water which is somewhere Tropic of Cancer at 60 degree altitude, the variation typically looks in this range. So, that means the temperature availability is more during certain duration, that is from the May to November. Width of that dome will be from this higher temperature at a given location. If you take month wise, higher temperature is felt in the month of close to August. So, that means in the month of August we have highest temperature, and that happens at tropical water, and the temperature is lowest in the month of January. So, basically this is the temperature difference that we are going to achieve across the month wise. So, with this concept we are now going to propose the first cycle, which is called as open OTC systems. So, open OTC system means ocean temperature energy conversion system. We have temperature difference on the surface of ocean and the deep water, that is first thing, that we call as ocean temperature difference. Now, why we call this as open cycle? Because we are using only a single working fluid, and cycle is open because your entry of fluid into this system and exit of the fluid into the out of the systems is same, and that is in this case it is nothing but your ocean water. In one case we have warm water inlet, other case it is the deep water outlet. Now, to look at this, if you just see this figure, so what we have shown is that just for a gaining geographical locations, if you see the surface of ocean water is available at 27 degrees centigrade and we are putting a deep water pipe, whereas deep water is close to 11 degrees centigrade and the depth could be approximately 1 kilometer. So, across this depth we have put a pipe which we call this as a deep water pipe. So, this temperature availability between this deep water and surface water is different. Now, we are having this power plant here. Now, what this power plant constitutes? It is an evaporator, there is a turbine generator assembly, we have a direct surface condenser and we have a cooling water circulation for the condenser. Now, how we are going to feed the water into turbine? So, first thing you see that what is the available temperature difference for us. First is warm surface temperature which is available somewhere in these locations. So, you take this as inlet, that is state 1 and which is available at 27 degrees centigrade and corresponding to its saturation pressure, if you refer the steam table, this number will be 0.0356 bar. Now, when it goes in, then it enters into an evaporator. Now, what does this evaporator do? That means, here this evaporator is normally operated at a low temperature much lesser than this, that means it is 0.0317 bar. So, the corresponding synonymous in the steam plant we call it as a boiler, but here we are using evaporator because our delta the dealing of working fluid is at lower temperatures, the evaporator is the most appropriate word, but evaporator and boiler they perform the same similar operations. Now, what happens after that? Then after removing some dissolved gases, the water, that low pressure steam enters but with very high specific volume, enters to the turbine at state 3 and remaining water gets discharged. So, basically speaking, we are separating the vapor part and liquid part in this evaporator and all this liquid part goes as a discharge. The vapor part enters as a low pressure steam with very high specific volume and it enters and expands in the turbine. Now, when this turbine after expansions it can expand close to maximum 15 degrees centigrade. So, from 25 degrees to 15 degrees centigrade it expands. Now, when it expands it enters into the condenser. So, basically the condenser gets circulating cooling water like cool deep water which is available at 11 degrees centigrade through a pump and then it cools that and finally it discharges the cool water. So, through this process this cycle operates and we call this as a Claude plant or Claude cycle. So, typically based on the water availability on the surface of water and deep water, the Claude cycle is defined. Now, coming back to this thermodynamic viewpoint of this, we see this particular temperature entropy diagrams. So, what we see that process 1 to 2 is throttling, that means from warm surface water to evaporator conditions it goes in the throttling manner, and from 2 to 3 it is a evaporation process. 3 to 5, 5 phase is an isentropic, 3 to 5 phase is an isentropic expansion in the turbine, but actual process becomes 3 to 5. So, and then from 5 to 7 it is a condensation process and again from 6 to 5 it again cycle continues. So, essentially speaking this is nothing but a typical Rankine cycle, and since this Rankine cycle was implemented in a low temperature systems by Claude, we call this as a Claude cycles. So, we will discuss more in this later part of this. So, I have already mentioned about the this explanation for this cycle arrangement. What we see is that when you most importantly what we see that when from 1 to 2 it is a throttling process, but from 2 to 4, one is that at this point what this evaporator does is it sends this vapor part to 0.3 and liquid part to 0.4, that means liquid vapor separation takes place, and from 3 we have this low pressure steam which is expands with till 5 and then enters into the condenser at its 15 degree centigrade. So, essentially speaking we have 10 degree temperature difference availability for running this cycle. Okay. So, this is all about this open cycle plant. Now, moving to the closed cycle OTC systems. So, here the concept remains same as it is, but only difference what we see that with respect to this heat engine perspectives that here we are using this working fluid as 3 parts like ammonia, propane or freon. So, these are called as low temperature cycles that uses typical working fluids like ammonia, propane and freon for their operations. Why we are saying it? Because if you compare steam to this part, we can see here that saturation pressure is for steam it is 0.85 at 4 degree centigrade and 3.5 at 27 degree centigrade. But same thing, that means if you use the steam as to be working fluid, then we must operate that evaporator at this low pressure. But when you choose other working fluids, then we have preferred choice that we can operate them at much higher pressures. So, when you operate them at much higher pressure, losses will be minimal and there is a probability of harnessing maximum potential of energy. Now, if you compare this low temperature cycle with respect to superheated steam, you can imagine that when you use a steam power plant, we are looking at operation of the plant about 16.5 megapascal 540 degree centigrade, specific volume close to 0.02 meter cube per kg as compared to very high specific volume value for low temperature cycles. So, these are the some of the advantages and one more important point that I need to emphasize, that whether we are using Claude cycle or Anderson cycle, under no circumstances we will have efficiency more than 25%. That is because if you look at this particular things at any locations, like let us say from one surface water to evaporator, we have hardly 2 degree temperature difference. Let us say we are looking at this exhaust from the turbine and cooling water, we have 2 degree temperature difference. Then we have deep water and cooling water entry to the condenser, you have only 2 degrees temperature difference. Now, within the 2 degrees temperature difference, there are issues like irreversibility and although we have maximum possible temperature could be 16 degree centigrade and 16 degree centigrade based on the availability of water, but we can only the possible way for exchanging heat availability is only 2 degree centigrade. But one advantage is that with that 2 degree centigrade things we can use large volume of water. Now, using that large volume of water for small temperature difference requires huge infrastructure cost. So, till this point of time, harnessing power from ocean temperature energy conversion is not yet to be justified because it requires a huge infrastructure and different technology. Although theoretically it is possible, but in fact due to its efficiency, less efficiency at higher infrastructure cost, till this point of time OTEC systems has not gained many attentions. So, with this this is all about that I need to speak about this ocean temperature plants concepts, Claude and Anderson cycles. Now, just to give a feeling of the Claude cycle and its applications, let me solve a numerical. Of course, this numerical problem will give you some emphasis on how you are using the similar concept of steam power systems in a Claude cycle, and essentially we are looking for a low temperature vapor cycle. So, here I have taken the same figure in which the system operates. Already I have told you that maximum available temperature difference, which is from one surface difference and deep water, it is 16 degree centigrades, but actual temperature which is available like between this evaporator and turbine exit, that is these two, is 10 degree centigrades. So, through this process there are irreversibilities associated with, and due to these irreversibilities we have polytropic efficiency for the turbine which is defined at 0.8, and turbine generator unit has a combined efficiency of 0.9. So, typically an OTEC systems produces 100 kilowatt gross power while operating on Claude cycle. So, when I say Claude cycle, we know that there is no change in the working fluid, that means same ocean water is being used as a working fluid, there is no separate working fluid, and we have all the numbers denotes the available temperatures we have, and through this process when you try to incorporate in this TS diagram. So, this TS diagram looks like this. We have from 1 to 2 is a throttling, 2 to 3 is a evaporation process, 3 to 5 is your turbine process, and 5 to 7 is your condensation process, and this is nothing but typical ideal Rankine cycle analysis, but similar to ideal Rankine cycle we are using the properties of water at different temperatures. This is the extract, and why I am taking only this temperature, because there we do not have any other possibilities to go any other temperatures. So, it is corresponding saturation pressure, specific volume, enthalpy and entropy. These data will be used to calculate to solve this problem. So, first thing, let us try to solve one by one component. We are looking at evaporator unit. So, evaporator unit we starts from the process 1 to 2 to 3. So, and that means from 1 it comes, from 2 it goes to 4, liquid part the separation starts, liquid component moves to 4 as a discharge, vapor component moves to 3 towards turbine. So, we can say since it is process 1 to 2 is a throttling process. So, which means H1 is equal to H2. Now, when you say H1 is equal to H2, we can write this H2 is equal to, what is H1? H1 stands as at this location, it stands as HF plus X2 into HFG, and this is available at 27 degree centigrade, and that is nothing but H1. So, from this data when you put, we write this as 104.8 which is HF plus X2 is unknown, HFG 2442 is equal to H1. H1 is available at 27 degree centigrade. So, 27 degree centigrade means what is 113.2. So, this will give you a number x2, that means dryness fraction at location x is location 2 is equal to 0.00344. So, it means that dryness fraction at point 2 is this. So, you take at this point you take this vapor out towards 3 and bring this discharge water towards 4. Then now another point is what was asked, that what the surface and deep water flow rate. So, for the time being we will assume that unit turbine flow rate let us say that is 1 kg per second, that flow rate. If you say warm water mass flow rate would be m dot w is equal to m1 by m2 m3 dot, and m1 and m2 are same, and this ratio becomes x2. So, that is that we are calculating for unit flow rate in the turbine. So, warm water flow rate is ratio is 290.7. So, this is for evaporator. Now, from evaporator we have moved to turbine. So, let us say what happens in the turbine. So, turbine process is typically reversible adiabatic or isentropic. So, we say H3 is nothing but Hg, because it is saturated vapor at 25 degree centigrade, and that is 2550. And this H3 and of course, at that point we have S3 is equal to 8.5147 kilojoule per kg Kelvin, and this process is isentropic. So, we can write it as a process 3 to 5s. We write it as S5s is equal to S3, which means SF plus x 5s into SFG is equal to that available, it is at 15 degree centigrade. So, you have to take this row and take the data at 15 degree centigrade, and that is nothing but your S3 8.5147. So, taking the data from 15 degree centigrades, we get from here x 5s is equal to 0.9739. Okay. So, at this location your x 5s is known. So, isentropic work that can be calculated as W dash isentropic is equal to H3 minus H5s. So, once we know X5s, we can find out H5s is equal to HF plus X5s to HFG, that is at 15 degree centigrade. So, from this data H5s we can find out as 2463.5 kilojoule per kg. So, we have H3 and we have H5s. So, this becomes 2550 minus 2463.5. So, we get isentropic work from the turbine as 86.4 kilojoule per kg. Then turbine work WT will be efficiency of the turbine isentropic into W isentropic work. So, efficiency of the turbine is 0.8. So, 0.8 times 86.4. So, this number is 69.1 kilojoule per kg. So, we have now turbine work, and this turbine work can also be interpreted as H3 minus H5, that is equal to 69.1 kilojoule per kg. We have H3, already H3 we have here. So, this will give you H5 number as 2480.9 kilojoule per kg. Okay. So, this we get from the turbine output. Now, we have this turbine generator unit. So, already turbine is giving WT is 69.1 kilojoule per kg. Now, efficiency of turbine generator is 0.9. So, actual power which is typically actual power would be 0.9 into 69.1. So, actual power becomes 62.2 kilojoule per kg. Now, this particular power is linked to this gross power. So, basically speaking, this power we need to correlate with the gross power to find the mass flow rate. But before to do that, we also need to do analysis for the condenser. So, condenser process is from 5 to 7, 5 to 7, 5, 6, 7 condenser and cooling water systems. Now, this temperature is known, cooling water state 6 is known. So, we can say what is H6 is equal to HF at 13 degree centigrade. So, this is 54.6, 13 degree centigrade HF kilojoule per kg. Then at this point also V6 specific volume is 0.001 meter cube per kg. Then we have H7. H7 is available at 15 degree centigrade. So, we say HF at 15 degree centigrade. So, this number is 63. Okay. So, we can find out the cold water mass flow rate per unit mass flow of turbine. So, that is m dot c is nothing but H5 minus H7 divided by H7 minus H6. So, this ratio to this ratio, and that is with respect to unit mass flow of turbine. So, this number is 2480.9 minus 63 divided by 63 minus 54.6. So, m dot c is a fixed number, that is 288.9. So, remember this number we are going to use further. Then move to cycle, complete cycle. So, for complete cycle we have information total power or gross power, which is 100 kilowatt, and we need to find out what is turbine mass flow rate. That is m dot t. Previously we calculated 100 kilowatt is your gross power, and W t we have already calculated as 16 point like 100 into 1000 divided by 69.1, which is the gross power, that is W t is 69.1 kilojoule per kg. So, this will give you m dot turbine flow rate as 1.447 kg per second. So, it is 100. So, 1.447 kg per second. Then we have already calculated m dot W as 290.7 and m dot warm water, cold water rate we have calculated as 288.9, and this is based on unit flow rate of turbine. So, already we find out what is the mass flow rate in the turbine to generate this gross power is 1.447 kg per seconds. So, this will imply warm water flow rate, which is our surface water, flow rate would be m dot T into m dot W. This is 420 kg per second. Then deep water flow rate, that is m dot deep is equal to m dot T into m dot C, that is 288.9 into this. So, this number is 418 kg per second. So, roughly you say that we deal with this kg per second flow rate of water, but effectively to produce a gross power of 100 kilowatt, which is with respect to this flow rate, this number is quite less. Now, if you talk about cycle efficiency, that is W dot T divided by QA, that means heat addition, and we have this number is 69.1, and heat addition, that is H3 minus H7, that means how much our maximum temperature, not heat addition, you say Q, the available temperature difference between this point and this point, that is H3 minus H7, that is 69.1 divided by 2550, and these values are already calculated, and H7 is 63, and this number comes out to 0.028. So, what it means is that by virtue of this temperature difference at location 3 and 7, and that is the maximum available enthalpy, and within this 10 degree temperature difference, your cycle efficiency is approximately 2.8%, and for power requirement and mass flow rate, this efficiency is quite less. So, this clearly indicates that OTEC plants have very less efficiency that involves very high infrastructures. So, this is all about to give a glimpse of a OTC plant and its cycle analysis. So, with this I conclude this lecture. Thank you for your attention.